let's create the inverse trig functions. So we'll start with inverse sine x. We're going to find the inverse function of sine x, so let's draw that up. And we know the domain is all real x, the range -1 to 1. However, it fails the horizontal line test, so it does not have an inverse. So we want to restrict our domain. We want to get a piece of this curve which is either continually increasing or continually decreasing. If possible, we'd like to grab 0 and as much of the positives as we can. So the piece that I'm going to pick will be from -π/2 to π/2. That'll get me the complete range. So the range will be unchanged. Okay, so y equals the inverse sine of x. Its domain, well, the range of the original function becomes the domain, so -1 to 1. And its range will be the restricted domain of -π/2 to π/2. When we draw it, it should be a reflection in y equals x, but because of the scale I'm using, I'm not going to put it on the same one. So it should reflect in there, but what we'll end up with is just a piece of the sine curve winding along the y-axis. Okay, so there's our inverse sine graph. And by the way, this explains why when you use your calculator to find an angle, it will only ever give you an acute angle or a negative acute angle, because the calculator is using the inverse sine function. Okay, let's do cos. So start with the original cos graph. Domain is also all real x, range is also -1 to 1, but I have to choose a different restriction. -π/2 to π/2 will be no good for this one because it will still fail that horizontal line test. So the piece I'm going to pick is actually one that's decreasing because I want the positives, I want 0, so I'm going to choose between 0 and pi. Again, that'll get me the complete range. So the range stays the same. So inverse cos x, the domain will be the original range, and the range will be our restricted domain, 0 to pi. Again, it should be a reflection in y equals x. It will look something like this. Again, it's a cosine curve, but winding along the y-axis. But again, notice this one. It only gives answers between 0 and pi. Or if we're talking about degrees, 0 and 180. So again, this explains why when you're using your calculator to find an angle, it will only give you an acute angle or an obtuse angle as an answer. All right, let's complete the set. We'll do inverse tan, our tan graph. So this is the one with the interesting domain where we have all the vertical asymptotes. Fails the horizontal line test. So pick a piece. I could pick any piece I like, I guess, because each individual bit is continually increasing. Logically, we'll pick the one that goes through the origin. So I'm going to restrict it between -π/2 and π/2. All real y will still be the range. So when we do inverse tan, domain and range swaps around. So domain is all real x for inverse tan, and the range will go in between -π/2, but not including, because we're still going to have those asymptotes there. But they will now be horizontal asymptotes when we draw it. So we reflect, and there's our inverse tan graph. So they're the three basic inverse trig graphs that we'll end up using. Some properties that helps us play with it. The inverse sine of negative x is equal to the negative inverse sine of x. Because if you have a look at that inverse sine function we drew, it's an odd function. So it must satisfy the rule for an odd function. This one's a little bit more interesting. Inverse cos of negative x is actually equal to a pi minus the inverse cos of x. Now that's because we don't have an odd function, but what we've got is an odd function that has been shifted up pi/2 units. And I'll show you in a sec why it's pi/2 rather than pi. Inverse tan of x, if you look at that graph, yes, it's also got the rotational symmetry. It's also an odd function, so inverse tan of negative x would be the negative of the inverse tan of x. And one other relationship, inverse sine of x plus inverse cos of x will be pi/2. Reason for that, you're basically talking about the angle sum of a triangle. Because if you think of a right angled triangle, one of the angles will be the inverse sine of x, and the other angle will be the inverse cos of x. All right, let me explain that second one then. So there's our inverse cos function. At this stage, it's not an odd function, it's not an even function, but if I was to shift it down pi/2 units, that curve is an odd function. And by shifting, we know the equation of that curve would be the inverse cos of x minus pi on 2. So that's an odd function. If it's an odd function, then function negative x must equal negative function x. So the inverse cos of negative x minus pi on 2 must equal the negative of inverse cos of x minus pi on 2. Well, playing around with that, we get our result. So that explains why it's a pi on 2 shift, not a pi shift, which sometimes people think when they look at it, it must be a shifting pi, but no, pi on 2. Oh, some alternative notions for inverse trig. I mean, I like the -1, but some people call it arc sine. So you'll see that in some books sometimes. Personally, not a fan. And some people even abbreviate that further and just go a sine, or a tan, or a cos. I think stick with the -1. It also explains why we have the reciprocal ratios, secant, cosecant, and what have you, because that does not mean to the power of -1. So with trig, you never put a negative power there, because it means something else. -1 is talking about the inverse function. Let's look at some examples. We will find the exact value of inverse tan of root 3. Now, because we're now dealing with the inverse trig functions, there is only one answer to the inverse tan of root 3. Yes, there are many angles that when you go tan of that angle that gives you root 3, but there's only one for the inverse tan function. So that's the one we want. It would be pi on 3, inverse tan of 1 would be pi on 4. And so a bit of arithmetic, we get pi on 12 for our answer. The inverse sine of 1 on root 2 minus the inverse sine of minus a half. I've gone this way. I've said inverse sine of 1 on root 2 is pi on 4. And then inverse sine of minus a half, thinking of the graph, that gives me a negative acute angle. So I'll get minus pi on 6. And we can work that one out, 5 pi on 12. I suppose the other way you could have done it is through that transformation. You could have said inverse sine of minus a half is the same as minus the inverse sine of half, and then minus minus becomes a plus, and you get pi on 4 plus pi on 6, and we get the same answer, however you choose to do it. The cosine of the inverse sine of 40 on 41. Now remember, inverse trig is an angle. So you're talking about an angle. We don't need to find the angle, because what I can do is I can draw myself up a triangle and say, well, if that angle there is the inverse sine of 40 on 41, then I know its sine ratio is 40 on 41. I can do a bit of Pythagoras, 9, and so now I know the cosine of that angle is 9 on 41. So I don't need to work out what the angle actually is. Other way around. Very, very careful with this one. Inverse sine of the sine of 5 pi on 6. Now you would think that the answer is 5 pi on 6, because inverses cancel each other out. When we go e to the power of log, or log e, they cancel each other out. Got to be very careful with inverse trig because of the restricted domains. Inverse sine of sine 5 pi on 6. Problem is 5 pi on 6 is an obtuse angle. The inverse sine function won't give you obtuse angles. So you've got to think, what would the equivalent answer be? Well, 5 pi on 6 is in the second quadrant. Sine is positive in the second quadrant. So going back to our basic inverse trig, it must be a positive acute angle that we want. So the corresponding positive acute angle for that one is pi on 6. Okay. So 17b, let's play with inverse trig.